Okay, we can get started here. So a couple of announcements before we dig in. So first, next week is the ASHRAE conference, American Society of Heating, Refrigeration, and Air Conditioning Engineers. So how many folks are going to ASHRAE? Yeah, it's kind of like half the people in the classroom right now. So I think in honor of that, I think we're gonna cancel class on next week, Tuesday. We will have class on next week, Thursday, though. And I may or may not put up a lecture video. I think probably I'll just push Tuesday's lecture to Thursday for that reason. I'm going to be at ASHRAE, at least for part of it as well. Okay, so that's one announcement. The other announcement is so we'll have the founder and CEO of a DER startup company called Flip that they operate basically various DERs to provide services to the power grid and to the users and homeowners and things like that that have the DERs. So he reached out to me, that this founder reached out to me on social media. And basically, I had been, posting about this class and posting lecture videos in case anybody wants to look at them and stuff like that. And he reached out and said, "Hey, are you interested for the class projects and real things that real companies are interested in?" And I was like, "Yeah, definitely." So he is going to come on Thursday, join via Zoom, and give a short presentation, basically about himself, what his company does, and then some projects that they have in mind, 2 or 3 different projects that they are kind of thinking about these days. And so, we won't necessarily have all the background to understand everything that he's talking about at this point, but as we get further on in the semester, we will learn all that kind of background and the tools to kind of solve, or at least approach solving some of the problems that he has in mind. So this is it's the only company that I have lined up so far for the semester to do this, but I think I would love to work with other companies as well, and other just researchers and things like that, people who have kind of more grounded projects. The idea being that, we'll eventually team up in teams of 1 to 3 or possibly 4 and do these projects. And so, if we have kind of 7 or 8 or 10 projects to choose from, then that makes it easier for, teams to choose topics and stuff like that. I know some of you will be doing projects that are maybe related to your own research, your MS or your PhD research, and that's great too. But for people who are more, kind of industry focused right now, having this company come in might be great. So, okay, so that's Thursday of next week. It won't be the whole time. We'll still do a lecture. We may not get through a full lecture like I'm doing today, but we'll at least get through much of it. Okay, so let me just, we're in week 2 here, or 3, I don't even know, losing track of time already, but let me just recap briefly what we've done so far. So the first lecture, basically I provided some background on DERs in general. We talked about what they are, some examples of them, and the kind of stuff we'll be doing in this class. And then we started kind of on the methodology section. We're eating our vegetables for last lecture and today's lecture. And last lecture, we talked about basically solving systems of linear differential equations, which it turns out is an enabling mathematical technique in order to simulate a lot of the DERs that we'll study in this class. So today we're going to talk about how you go from basically differential equations land to what's called linear systems or linear dynamical systems land. So the idea here is that we have some physical system. Actually, it doesn't have to be physical. It can be a cyber type system or economic system, something like that. But it evolves over time. And it does so in a way that can be described by linear differential equations. So then we'll talk about essentially methods for simulating that and so forth. That's the topic of today's lecture. And this is really the second and the last of this kind of core mathematical background. And then the following lecture, which again won't be next Tuesday, but next Thursday, this Thursday's lecture, we will start talking about actual DERs. We'll start with batteries and electric vehicles. Okay, so we'll right away start applying the stuff that we did in this lecture and the previous lecture to real problems. All right. But yeah, today, linear dynamical systems. So we'll start talking about them in what's called continuous time. This is basically what we do in a differential equations class or a dynamics class, something like this. We'll talk about linearizing systems that are described by nonlinear differential equations. And then we'll talk about moving from continuous time to discrete time. So rather than having a smoothly varying time variable, you have one that's essentially integer valued. So, you might talk about hour 1, hour 2 through hour 24 of a day, for example. And then I want to save time for this. I'm excited about this example at the end. So we'll talk about a simple model of Earth's climate that basically shows how greenhouse gas emissions affect global average surface temperatures. And it turns out that that's a nonlinear system that can be described by differential equations, but we can linearize it and simulate it using basically the tools that we talked about in the last couple of lectures. Okay, so first of all, what is a linear dynamical system? So here, basically, we have the kind of fundamental description of one of these kind of in its most general form. So on the left-hand side here, we have the time derivative, where t, again, is kind of a real valued, a smoothly varying thing. We have the time derivative of x, which is known as our state vector. And in general, this can be nx dimensional. Oftentimes we'll deal with one-dimensional states if we're thinking about just the energy in a battery or something like that. But more often we can also find, higher dimensional things. You could have a bunch of batteries all interacting together, or you could have a battery and a water heater and a building and stuff like that. So dimension of x can grow quickly. And then A here is called the dynamics matrix. So essentially it maps the current state into the derivative, the time derivative, its rate of change. And then U is typically viewed, so both U and W are sort of viewed as inputs to the dynamical system. So you have the state of the system, which, in a physical system, like in a dynamics class, that might be just a list of positions and velocities, right? Or angular velocities, something like that. Or in our systems, it might be energies, temperatures, potentially pressures, things like that. And then the inputs in general, both U and W, are things that kind of drive that system. They force some behavior out of that system. And the reason we differentiate between a U and a W is basically U are things that we can control. We can manipulate them directly. So U is often called either the control input or just the control or the action. So in a reinforcement learning class, they talk about very similar things, but they use a little bit different vocabulary. So action is typically used for U rather than, and they'll use the symbol A rather than U, but it basically means the same thing, things that we can directly manipulate. And then W is, again, an input to the system that kind of forces the system, but it's stuff that we can't control. So things that are called exogenous, or they may be random, they may be uncertain in some way. And those disturbances could be, in our problems, it might be things like the outdoor temperature. It might be behavior of users who are, drawing water out of a water heater, or who are changing the temperature set point inside of a house at the thermostat or something like that. In a dynamics type problem, right, where you're dealing with the motion of a rigid body, say a disturbance could be maybe wind that's buffeting a plane as it's flying around, or things like that. And then we call B basically either the control matrix or the action matrix. And so B maps the inputs that we're controlling into basically changes, or sorry, the rate of change of the states. And the dimensions of these things all need to be consistent, right? So if NU is the control dimension, then this matrix B here needs to have a dimension NX by NU. Okay, so already this general modeling framework can cover an enormous variety of stuff. And we'll see that although it's not perfectly general, the more general version of this would have sort of just a nonlinear function on the right-hand side of X, U, and W. But we'll see that a linearization of a system that's put into this form, this kind of linear form, can actually model a lot of nonlinear systems pretty well. Not perfectly, but pretty well. Okay, so that's kind of what's called the perfectly observed case, where we basically, we're only looking at the evolution of the state itself, and we assume that we can actually measure or observe everything within that state vector. But oftentimes we can't sort of see or observe or measure everything that's inside of X. And so we might have what's called an output equation or a measurement equation. That's the second equation that shows up here. And so here, Y is the observation, also known as the output or the measurement. And then this matrix C essentially maps states into measurements. And then this term actually often drops out. We often don't need it, but I put it in there just for generality. We also, in theory, could be measuring basically linear functions of the inputs and things like that that we're putting into the system. And then V is typically known as noise. And, classically, this kind of system might have been used to measure, something happening in an electrical circuit or something like that. And so V often has the interpretation there as a sensor noise from a voltmeter or a current meter or something like that. For our purposes, we might, for example, in a building control problem, X might be a list of temperatures inside the fabric of the building. So it could be the air temperature in a bunch of different rooms, but it could also be, the temperature inside this wall behind me, for example. And in a setting like that, we would have access to measurements of the air temperatures, but not to like the concrete temperature and stuff like that, because people typically don't put sensors in there. But so an output equation like this could describe that essentially. And then again, in that same example, maybe our temperature sensors might be a thermocouple or a thermistor or something like that, and they might have a fraction of a degree Celsius of noise, essentially, that comes from inaccuracies and things like that in the circuit that measures things. Okay, so this is kind of the full system in all its glory for a linear time varying system where these matrices A, B, C, and D have time variation in them. Very often, A, B, and C, D do not depend on the time variable T, and in that case, we call it a time invariant system or an LTI system, linear time invariant. Often we'll have one input and one output, so sort of scalar equations. And actually in this single input, single output setting, you can still have a high dimensional state vector. It's just that you're only sort of measuring one thing and you're only kind of sending one input to the system. And again, very often we have no feed through, so this D matrix is equal to 0. And here, again, this equation is a little bit ambiguous, but we need to recognize that here, Z0 is not the scalar 0, it's actually a matrix of dimension nx by nu, where every element is a 0. And then the perfectly observed case, we started with that on the first slide. So there, basically, we're saying that the observation is equal to the state. So we have perfect noiseless measurements of every single variable in that state vector. And then often we'll deal with what are called deterministic systems, which means you have no disturbance. So you have control over every input that's fed into the system, and you have no noise either. So often we'll deal with these kind of greatly simplified cases, but I just want to sort of lay out the general framework so you guys know. Okay, so that's what linear dynamical systems are. Let's talk about linearization, because again, the world is nonlinear. If you do physics to get governing equations for some system, you'll usually end up with nonlinear differential equations. So how do we turn those into linear differential equations? So just a little refresher for your memory here. So when we linearize basically a function of one variable, a single valued function of one variable, or a scalar valued function of scalars is another way to say that. So suppose and I'm not talking about differential equations here, just linearization of a nonlinear function, right? Just as a reminder. So we have some function f that maps scalars, real scalars into other real scalars. And we imagine that it's differentiable at some fixed point x hat. So this is just a number, 27 or negative 3.5 or whatever it is. So from Taylor's theorem, we know that basically this function f at x hat, or in the neighborhood of x hat, can be well approximated by a linear version of a linearization of that function. So that's just f, the value evaluated at x hat, plus the derivative f prime times the difference or the deviation of x, the variable, from that x hat, 2.7 or 39 or whatever it is, where we're linearizing. So here, classic picture, you've all seen this in calculus and so on, but this is what that looks like. We have x on the horizontal axis. This curve here is f of x, which is just x squared in this example. And we're linearizing about the point x hat equal to 1/2. And so we can compute that linearization. The derivative here is just 2x. So if we evaluate that at x hat, we get 2x, 2 times 1/2, which is 1. So derivative is equal to 1. F of x hat, well, that's 1/2 squared is 1/4. So we have 1/4 minus 1 times the quantity x minus 1/2. And so that ends up being just x minus 1/4. Okay. So you can see that we're matching the slope, right? And we're matching the point as well. But as we get further away, the deviation between the linearization and the function itself grows. Okay, so that's for scalar valued functions. Now let's think about vector valued functions that take vectors as inputs. So kind of same setting, but here we have a function that takes n-dimensional vectors as inputs, and it outputs m-dimensional vectors. So one way to think about this thing, f, is this object is basically a list, a stacked vertical list of functions that take n inputs and produce one output each. And again, we make the assumption that f is differentiable at this particular point x hat. And then again, from Taylor's theorem, we get that in the neighborhood of x hat, f is well approximated by its linearization. And here, the linearization is somewhat more complicated. So now f of x hat, well, that's a vector in Rm. And this d thing here, rather than having an f prime like we had in the scalar case, we have a df. And this is the derivative matrix, or what's called the Jacobian matrix of f. And again, we're evaluating it at the point x hat. And now we're doing matrix vector multiplication between this, I guess, n by n matrix and then an n vector here. Sorry, m by n matrix. Okay, so the definition of this derivative matrix is just a list of all the partial derivatives of f. And so we start with the function f1. And this row basically is the, if you remember from vector calculus, this is the gradient of the first function f1. So it's df dx1 all the way through df dxn. And we evaluate all those derivatives at the point that we're linearizing about, the point x hat. And then so that's the gradient of the first function, and then we just kind of march down until we get to function m of f. And then we have the gradient of fn here. Okay, so far so good. Right. Okay, so now let's see about applying that linearization of vector valued functions with vector inputs. Let's apply that to the case where we have a nonlinear dynamical system. So here, in the linear case, we had, again, dx dt on the left-hand side, and x is a vector in Rn x, potentially. And then on the right-hand side, rather than having kind of an ax plus bu plus w, we have just some generic function f. And it takes as inputs a state vector, an action vector, and then a disturbance vector. And so those are in Rnx, Rnu, and Rnw. And then the output of this function f, again, it's a list of a bunch of functions that produce scalar outputs. And so the overall output of this function f is itself a vector in the state space, basically dimension Rnx. Okay, so now we suppose, and I'll talk about where you might get this, but we suppose that we have some solution, x hat, u hat, and w hat, that satisfies the original differential equation. So we call these things nominal trajectories. So at any particular time, if the input is exactly u hat, the action is exactly u hat, and the disturbance is exactly w hat, then we know we follow this kind of path through state space. And we follow that trajectory x hat. Okay, so again, we'll talk about where these things come from, but suppose for now that we have these hat trajectories. And then we define the perturbations, basically little nudges, little deviations away from these nominal trajectories. So by the way, the terminology trajectory comes, from like the 40s, 50s, and 60s when, most engineers were working on space race kind of stuff. And so people were thinking about, how do you send a shuttle or something like that, a ship basically in space, from Earth to slingshot around the moon and then go to some planet or something like that, right? So, they map out these trajectories, but of course the calculations aren't perfectly correct and stuff like that. So you have these deviations from the trajectories, and then they design control systems to basically try to knock the ship back onto, the trajectory that it was launched on originally, things like that. But okay, so we define these perturbations, which is just the actual value of the state minus the nominal value at a particular time. And then we do the same thing with the action and the disturbance. So then we can just write down the derivative of the state perturbation, or deviation delta x. And so that ends up being, by linearity of the derivative, it's just dx dt minus dx hat dt. And so that's exactly f minus f of x hat, u hat, and w. And now if we're close to the neighborhood of these nominal trajectories, then the derivative here, the difference of f evaluated at some generic x and f evaluated at the nominal x hat, the difference between those things is well described, it's well approximated by this expression here, which is linear in the deltas, linear in the perturbations. And it turns out if you just apply what I wrote down a couple of slides ago for taking derivatives of these vector valued things, you get the definitions of these matrices A, B, and G. And they end up just being the entries, the elements of that derivative matrix or the Jacobian matrix that I showed, which had basically all the gradients as row vectors. So here, for the dynamics matrix, the A of t, we get that its ij element is the derivative of fi with respect to xj, and then we evaluate that derivative at the nominal trajectories. And then the other matrices are defined similarly, but they're the derivatives of f with respect to the action variables and the disturbance. So the point here is that basically we had some nominal profile or trajectory that the system was following. And then we say if we kind of stay near that, but we're not exactly on top of it, we define these little perturbations away from it. And then the dynamics of that kind of perturbation system are well, in fact, very well modeled by this linear time varying system up here. Okay, and then again, this thing looks basically like that first slide that I showed. That sort of ax plus bu plus w on the right-hand side, except here we have deltas instead of the actual kind of absolute numbers. We'll go through all this stuff in a more concrete example in a few minutes. But so who has seen this kind of like linearizing around trajectories, maybe in a dynamics class or something like that? Two or three people. Okay. And for whom is this kind of brand new? It's okay. So, yeah. Another half the class or so. All right, good. Okay, so there are kind of two mathematical operations that involve some degree of approximation that we're doing here. And one is going from a nonlinear system to a linear system. And then the other is going from a continuous time system to a discrete time system. And we'll talk about now how to do that discretization. Okay, so once we've arrived at a linear dynamical system, we have good tools that can simulate it. And those tools typically want us to use discrete time framework rather than a continuous time framework. So everything on a computer is discrete, right? It's all kind of ones and zeros. So the way that we typically do that is we take a time span and we just kind of divide it up into chunks. And they don't have to be equal chunks. So you can imagine if you had some system where there was a lot of action, really fast oscillations happening during some portion of the time span, but then it was really slow and smooth during some other portion of the time span. You can imagine having high resolution in your time discretization kind of in that busy portion, the active portion, and then using longer time steps in the kind of boring portion. So you can do that, although what people almost always do is just use uniform time steps. Okay, so here capital K is the number of time steps that we've divided up our time span into. And then this notation here just means the set of, and when it just has a comma delimited list inside, it just means the set of a finite number of elements, basically. So this would go from 0, 1, 2, all the way to whatever K is, 100 or something like that. And then very often we use a constant time step and call that delta T. For DER simulations, often that'll be an hour or 15 minutes or something like that. And then if we do that, then we get an expression for what each of the times are. It's just the initial time plus K times this length or duration of the time step. Okay, so now this is where basically the material that we learned last lecture about linear differential equations, systems of linear differential equations, this is where that comes in. So this is just a refresher of equations that we learned last time. But here, if we have a vector linear ordinary differential equation, ODE, with an initial value problem, meaning we're given the initial state at the initial time, and it's a linear system, so dx dt on the right-hand side is ax plus b on the left-hand side. And we need the further assumption that this a thing is time invariant, so it's not changing over time. Then we have this nice analytical formula for what the solution at any time t beyond that initial time, what the solution to this differential equation is. And so it's the matrix exponential times the initial state plus another matrix exponential times the integral of this thing in here. And the stuff inside the integral here, this is a vector, right? We're multiplying a matrix n by n by, an n vector here. Okay. So that'll come into play. So suppose that we have this linear dynamical system. And this is the general form that I started with on the first slide. And then, we make the further assumption that A is constant over each time step. So it may be changing kind of over time, but it's doing it in kind of stair-step fashion. So over, within any particular time step, it's constant. Then we get this formula, and you don't have to write it down. It's a little bit messy, but basically this formula is just taking the solution that I showed on the last slide and plugging in values that let us go from time step k to time step k plus 1. The idea is if we know the initial state and if we know how to jump forward one time step, well, then we know the first state. And to get to the second step, well, again, we know how to jump forward one time step. So we use state 1 to get state 2 and so forth. And then we kind of march through the time span just doing that process. Yeah, so again, this looks like a hairy, nasty formula, but basically if you just take the initial time and plug in tk, and if you take the final time, t, and you plug in tk plus 1, and then you take this b of t that showed up kind of in the linear differential equations slides, if you take that and you turn it into basically matrix bu plus w, then you get this formula up here. And so in general, that's kind of what we would do, where we have some wiggly weird u, and it might drive the state vector through some series of changes that look kind of like this. But again, so I'm highlighting the important formulas, and you probably noticed that none of these formulas on this page are highlighted, and that's because they're not very useful. They're sort of hard to compute, hard to evaluate. So we need to know the exact expression, for example, for u and w at every time, not just the initial and the final time, but at every time in between them. So we'd need some function of time for them, sine of t, and over here we have e to the minus t squared or something like that. And usually we don't have that. Usually we just have data, sort of sampled data from u and from w. So in that case, what people typically do is that they assume that everything, all the sort of inputs to the system and the system matrices are constant over time. So before we were assuming that just the A matrix was constant, but now we're assuming that all of them are constant over time steps. And so again, there can be bulk changes in these things over the full time span, but within any time step, they're constant. Okay, so then we can, again, plug this stuff in and we get a slightly simpler looking version of our formula, the bu plus w, because that is all constant. Between tk and tk plus 1, it pops outside of the integral. And the only thing time varying, the only thing that has tau dependence on it inside this integral over tau is the stuff inside the matrix exponential. And then if A is invertible at time tk, then this stuff, the matrix exponential times this integral term, all of that simplifies, and we just have an e to the at minus the identity I times A inverse. And so this again comes from the slides that we presented last time, worked through last time. Okay, so what does that look like graphically? So now, rather than having this wiggly weird u in between time steps, here we're assuming that it's piecewise constant. And so we know the value at time 0, we call that u0 or ut0, and that's constant over the whole time step, and then it goes through this kind of step change down to value t1, that it's constant for a while, and so forth, all the way to the end of the time span. Okay, so to summarize, we begin with a continuous time linear dynamical system. And here I'm putting tildes on things that denote the continuous time version, because the one we'll work with primarily is the discrete time version. So let's use lighter notation and get rid of the tildes for that one. So we have an ax plus bu plus w in continuous time. And then these A, B, U, and W, all these things are piecewise constant over every time step. In that case, now we get a nice useful formula, which is that the new x, the x at the next time step, is equal to A, and this is the discrete time dynamics matrix, which is different from A tilde. Okay? But it's A of k times x of k, the state at time k, plus B of k, U of k, and then plus a new thing, W of k, which is, again, different from the continuous time disturbance. And then here, the notation, like, for example, A of k, it's just a lighter way to write A at the time tk, right? So we just drop the subscript and the t and stuff and just use the index itself. Okay, and then this thing A, we have a formula for, so it's e to the delta t times the continuous time dynamics matrix. And then we have formulas for B and W, but these are usually not very useful, again, because they involve this integral, and we'll find simpler formulas for that in the case where this A tilde is invertible. So MATLAB has built-in toolboxes. It's called the control systems toolbox that allows basically automation of most of this stuff. So you don't actually have to program in, matrix exponential and all the products and the integrals and things like that. Instead, you can just use these built-in functions. So here is MATLAB code that basically does the discretization of a linear time-varying system in continuous time to the equivalent discrete time system. So we start with this command SS, which stands for state space, meaning we're defining a dynamical system, and there are various ways to describe a dynamical system. You can do kind of an input-output, or impulse response. There are things like that. But typically, what we will use is the state space representation. So this defines a MATLAB object called a state space system, and we give it the matrices A, B, C, and D. And so the T here basically denotes a tilde. So this is stuff that comes up in the continuous time description. So this basically just defines the system, and then we call on that system C, C for continuous time. On that continuous time system, we call the function C2D, which stands for continuous to discrete. So C2D of the continuous time system, and then we give it a time step, which is just the difference between the new time and the old time. And often this would just be a constant, a delta t, but in general, it could vary. Okay, so C2D basically does this, process of computing the matrix exponential and the integrals and all that stuff, and then it gives you back an object, which is again a state space object, but now it's MATLAB knows basically that it's a discrete time system rather than a continuous time system. And then in that object, there's a field called A, which is just the dynamics matrix. And so, for example, if that's what you're looking for, you can pull it out here and get AK by just doing dsys.a. And similarly, if you wanted the B matrix, the control matrix for your discrete time system, you just do dsys.b. And you will do a little bit of this in a homework assignment that is coming up within a week or week and a half, something like that. Okay, and then if you don't want to use these built-in functions, or if you want to work in a different language or something like that, then you can do this yourself. So as long as the continuous time matrix A tilde is invertible at time k, then we get these explicit formulas for A, B, and then for the discrete time disturbance W. And they involve the matrix exponential, and then kind of a matrix products and inversion, things like that. But this is something that you can program in another language if you want to. And I think other languages, I'm not as familiar with Python or Julia, but I'm pretty sure they have this kind of discretization functions built in as well. Okay, so that was discretizing linear systems. And that is doable quickly, efficiently, very reliably, basically because we have an analytical solution for linear differential equations and systems of them. But as you guys know, I think we talked about this last lecture, nonlinear differential equations, we do not in general have an analytical expression for the solution. So we want to do something computational instead. And the way that we do that is by using basically a numerical solver for ODEs. And there are a whole bunch of those. The simplest one is called the forward Euler method, where you kind of just take the derivative and multiply it by the time step and add it to the old state to get an estimate of the new state. And that works okay under some conditions, but it's not super stable numerically, and sometimes it can blow up and diverge and so forth. So a better thing to use is what's called the Runge-Kutta fourth order method. And if you've taken a class in numerical analysis, you've probably used it, because this is essentially the go-to method for the vast majority of differential equations for solving them in reality. There are some methods called stiff, or some problems called stiff problems, and others where you might want to use some kind of other method, but basically ODE 4.5 works really, really well almost all the time. And so so that basically provides a way to discretize a system. If you know the state at time 0, and you have the differential equation, and you have the input data, you can use a nonlinear differential equation solver to basically push that solution forward through time until you get to time 1. And then you just do it again forever, essentially. And that's your numerical solution. Okay, so here's an example. I just made up one relationship between the state, the action, and the disturbance here, and they're all scalars in this expression. And in general, like in the example I'll show in a minute, we'll have a different, different looking thing for f. But the idea is here you first describe, in MATLAB syntax, this is called an anonymous function. So this says you define a function which takes as inputs a time variable, and we're calling it tk, and a state variable, call it xk. And then it computes this stuff, and it returns essentially the output of these calculations. So it takes the x, multiplies it by the u, and raises it to the power of the w. So this is, in general, this function f can vary because u and w are time varying. So at time 1, we might have one kind of version of f with u is 3 and w is 7. But at time 2, we might have u is -12 and w is 1.1 or something. So the function f is a time varying thing, and that's why I give it an index k here. So you take this thing, and then you call ODE 4.5. So 4.5 stands for Runge-Kutta fourth order. It has some sort of fifth order error analysis or something like that. But this is basically the go-to ODE solving function in MATLAB. You give it this function, the sort of right-hand side function, which is just this stuff. And then you give it the time span, the initial and the final time that you're interested in. So this would be tk, and then tk plus 1. And then you give it the state that you begin with, the starting state. And this thing solves the nonlinear initial value problem and returns a solution, which actually is a big vector of solutions, or potentially a matrix if x itself is a vector. And anyway, and it'll be evaluated at a bunch of times in between the initial time and the final time. And it won't be kind of at a regular array of times. It'll be a kind of a weirdly chosen array of times, something like that. And so then you want to just pick out the solution at the very end time. And I think I was doing this with a scalar valued f. With a vector valued f, this solution thing, again, would be a matrix. And so rather than just having end here, which would pick out just one element, you would have like all rows and the end. And that would pick out basically the last column of the solution. Okay, so I'm not going to talk about how this works. Again, if you take a numerical analysis class, which I think you should, I think it's kind of cool and fun, but also really useful. But if you take a class like that, you'll learn about this particular method, why it works so well, and stuff like that. So just out of curiosity, who's heard of the Runge-Kutta fourth order method before? Okay, so about half the class. Okay, when I mentioned before, I just want to go back to this slide. When we were talking about linearization, so in this step here, I said, suppose that at each t, we have some x hat, u hat, and w hat that we know satisfy the differential equation. And I said, I'll talk later about how we actually do that in practice. So, so sometimes if you know the exact, if you know a solution of this thing, or you've solved your nonlinear ODE analytically, and you wrote down some functions of time, that's one way to get the x hat, the u hat, and the w hat. But more often we can't solve the nonlinear ODEs. And so instead we use the Runge-Kutta method basically to generate this x hat given data for the inputs that we put into the system, the disturbance and the action that we put in. So you run your Jakarta solver or some other ODE solver to get these nominal trajectories, and then you form the perturbation system about this. And I'll show in the example kind of how some of that stuff works. Okay. So now we get to do a fun example. Does anybody have questions before we do that? Yes, please.
Slide 11 and 13 and each other. We have two different types of the state that visualizing. But our state variable behaviors are all the same. So it doesn't mean like it doesn't matter what kind of that it was very high. Like, it does not change in state.
So that's a really good question. Let me repeat it for folks who are on Zoom. So the question is on slide 11 and on slide 13, the control inputs look quite different. On 11, we have these wiggly functions of time. And on 13, we have these stair-step function, right? This piecewise constant function of time. And yet, if we look at what's happening in the top plot, the state trajectory here, it looks exactly the same. So what's going on there? And it doesn't mean that the way that we describe the inputs doesn't matter, because we're always going to get the same state behavior out of it. And the answer is no. So what's going on there is that I drew these things, and I just reused the same plot on slide 11 and slide 13 for the state plot there. So in reality, I don't know, like, if you imagine that there's some differential equation that relates the input u to the evolution of the state here, like maybe this thing actually should have some wiggles going on. And then down here, maybe this one should be smooth like it is. So I think in a future version of these slides, I'll probably go back and revise that so it's not deceptive in that way. But good question. Thank you. That's very, very sharp. Any other questions on this stuff? Yep.
Slide 16.
Mhm.
So, yeah, I'm just asking like function. Like, is there any reason why that function?
This particular thing that I chose here? Or do you mean, is there any reason that I start with this line?
Yeah.
Yeah, so ODE 4.5 requires, as one of the inputs, a function that it can use to evaluate the right-hand side of the differential equation while it's doing its clever numerical analysis process. And so I think actually you can write your own function, like a MATLAB function, create a new file, put some comments in there, and then say function right-hand side or RHS equals, and then you basically would put the calculations that go in to the right-hand side of your ODE, put those into your subfunction. And then you could save that file and you could pass ODE 4.5 the name of that file. So that would be one way to do this. It's usually simpler. Like in other programming languages, you can, within a script or some other function, you can define sort of a local function in that scope. MATLAB doesn't let you do that. Doesn't let you put a function definition at the bottom of a script, for example. And so if you just create a bunch of new files for everything you want to do, it can lead to like a sort of cluttered workspace. And so this is basically just a way to do that process without having to create a new file. So that's why it's called anonymous. It's like a nameless file that MATLAB just stores in memory rather than creating its own file. Does that make sense?
Yeah.
Okay. All right. Good. I guess I'm trying to get a handle on what folks have done before. So who has used something like an ODE 4.5 thing in a class to simulate some system? So what class? A robotics class. Was that here or an undergrad? Okay. Has anyone else like used a numerical differential equation solver for any engineering purposes? Yeah.
Yeah, I did ME 581, so we had to like do it all from scratch.
Oh, okay, cool. ME 581. So that's the numerical methods class. Okay. Okay. Cool. Okay. Well, that's good. And again, it's totally fine if you haven't seen this stuff before. I don't expect you to have seen it before, right? I'm just trying to gauge where we're at. Okay, so great questions. Any other questions about the material so far? And by the way, folks online, please feel free to chime in if you want.
Do you recommend using MATLAB built-in functions over customized and created functions?
So the question is, do I recommend using MATLAB built-in functions for things like ODE solving or for the time discretization, or writing your own stuff? I think like good practice in software development is always to use existing solutions, as long as they're good enough and they serve the purpose that you want, right? So it's hard to create and debug your own general code for solving some generic differential equation. There are just lots of edge cases and things like that are hard to test for and so on. And so this method, this ODE 4.5 function, has been tested and used extremely widely, and so it's known to be robust and stable and fast and so on. So yeah, I would say use it whenever you can. Of course, if you're in a ME 581 class, you have to write your own code, but you should even in a setting like that, I would say benchmark it against the MATLAB built-in function. Make sure you're getting the same output, and you can even compare the speed. So MATLAB has these functions tick and talk, which basically you can say tick, and then it essentially gets the clock time when the code begins that chunk of code, and then talk, it basically captures the elapsed time between your tick and your talk. So you can time how long it takes to actually run chunks of code. So for example, if you programmed your own version of the Renji-Kutta 4.5 thing, using for loops and stuff like that or whatever, you could benchmark the timing of that against what MATLAB has done. And probably the MATLAB thing will be a lot faster just because they put a lot of time into optimizing the runtime and stuff like that. So yeah, I think for this, I would definitely recommend. And again, there are other ODE solvers, and you can read MATLAB's documentation. There's like ODE 2.3 and stuff like that, other functions for stiff differential equations, but we probably won't encounter any of those. And then for the discretization thing, I think, yeah, I would encourage using the C2D function as well, just again, because it's known to be accurate. And when you try to write, all this stuff out with these integrals and inverses, or not integrals, but the matrix exponentials and the inverses and all that, A, it can be slow, and B, it's more likely that you make some programming mistake and get a wrong answer or something like that. Okay, good questions. Thank you. How are we doing on time? Just fine. All right. So the example that I want to do here, it's not a DER, but again, it's the thing that provides a lot of motivation for the work on DERs that we're doing. And so I want to just talk a little bit about a climate model that is, of course, much less sophisticated than the actual climate models that scientists use to write reports about global climate change and things like that. But it is accurate enough to give us kind of reasonable estimates of things like how greenhouse gas emissions affect the climate. And then in particular, it's relevant to today's lecture because we get a nonlinear dynamical system out of it, with inputs, things like the emissions that we're putting into the system, and then a state, things like the temperature of the planet. And so it provides kind of a sandbox where we can try out the discretization of time, we can try out the linearization and so forth. So just again, for kind of to gauge where we're at, who has done any form of climate modeling or like seen it in a class or anything like that? Okay. Cool. Good. So then this should be interesting to you guys, I hope. Okay, so here is basically the simple model, and this is kind of the simplest model that I could come up with that still is reasonably accurate and kind of interesting for our purposes. So the idea here is that we have the Earth described through two things. One is the atmosphere, right? And that's just drawn as this kind of thin gray layer up here. And the other is the surface of the Earth. And I'll show in a minute that you can approximate that basically with a sort of limited depth of water, right? Earth's surface is mostly water, so we use that. And then there's energy transfer between all these things. So the orange here is shortwave radiation, so sunlight, basically. And then the red here, this indicates long wave radiation. So for people who have taken a heat transfer class, you know that anything that is above absolute zero temperature is constantly emitting thermal radiation. and the emissions of thermal radiation are proportional to the temperature of the thing to the fourth power. Right. So Feng, for example, I know that you have been thinking a lot about this. So Feng does research on thermal comfort and how radiation affects, change thermal comfort of people in spaces, things like that. But so anyway, so let's walk through what's happening here. So we have sunlight coming in. This is from the sun, right? And so R, I'll show what these values are, but R squared, R is the radius of the Earth, and S is what's called the solar constant. So if you send a satellite out to space and you measure the energy intensity, basically the power that's coming to Earth per unit area from the sun, you get this value S. And it's about 1.3 kilowatts per square meter. So if you put a solar panel out in space and you faced it directly at the sun, it would just be producing 1.37 kilowatts kind of forever. There's a little bit of variation in this thing, but it's constant enough that we call it the solar constant. So R is the radius of the Earth. And so this pi R squared, well, that's just the surface area. Nope. We'll talk a little bit more about this stuff, the solar radiation stuff, when we get to the section on solar. But basically what this is the cross-sectional area of the Earth. So if you looked at, if I was to hold up a sphere here and shine a flashlight on it, it basically would have a circular shadow. And so this is the area of that shadow that's cast by the Earth, basically. Okay, so then if we take the area of that disk, we multiply it by S, we get the total amount of power, right? Watt per square meter times R squared would give us a square meter, or sorry, just a watts. So this is the total amount of power that's coming in from the sun, essentially. It's hitting all of the Earth, its entire surface. And then the atmosphere reflects some of that. And this thing alpha here is known as the albedo of the Earth. So it's basically how shiny the Earth is. So if alpha was 1, then all the sunlight would bounce back into space. It'd be like the Earth looked like a mirror from space. And if alpha was 0, the Earth would look black in the visible spectrum. Okay, and then the remaining fraction, 1 minus alpha of that initial amount that came in from the sun, the remaining fraction of that goes down and hits the Earth's surface. And in reality, there would be reflection and scattering. You would have like stuff bouncing back and forth, and you'd have more of it being filtered through the atmosphere back to space, but we're not sort of modeling those effects here. So basically, this energy gets absorbed by the Earth's surface. That makes the Earth hotter, and so then the Earth emits thermal radiation. Again, that's proportional to T to the fourth. And sigma here, so T is just the surface temperature, global average surface temperature of the Earth, and sigma is what's called the Stefan-Boltzmann constant. And that again, if you've taken heat transfer, it plays a big role in radiation heat transfer. And then 4 pi r squared, forget where the 4 comes from, but pi r squared again is the basically the surface area here. Okay, so some of that thermal radiation goes through the atmosphere. And then the atmosphere itself is at a temperature T with a subscript A, TA. And so we have basically the atmosphere radiating upwards and downwards. And the atmosphere, we assume, has an emissivity, little epsilon here. So if epsilon is equal to 1, that means the atmosphere radiates as a black body. And if it were 0, there would be no thermal radiation from the atmosphere. And then we're assuming basically the radiation leaving the Earth has an emissivity of 1. So the Earth radiates like a black body from the surface. Okay. So that's basically the model. Questions about the setup before we get into doing a little bit of physics and getting the equations out. Okay. All right, so some assumptions here. First, the atmosphere we assume is very thin, and it has basically no mass. So its temperature changes instantly as the forcing changes. And then we model Earth's surface as basically 70 meters of water covering 70% of the surface. And I don't know exactly why we use those numbers. So 70% of the surface is basically, that's how much of Earth's surface is covered by water. Why we use 70 meters exactly, I'm not quite sure. This I pulled from a climate scientist website. So presumably they had good reason for making that approximation. So then the internal energy, if we use what's called the incompressible substance model, for those who've taken a thermodynamics class recently, we get that the internal energy of all that water is just its thermal capacitance C times its temperature. And so that thermal capacitance is the mass times its specific heat. And that's the density times the volume times the specific heat. And you can crunch the numbers and you get about 10 to the 23 joules per Kelvin. So that's just, again, the depth of all that water and then essentially the length of it. So now we'll do a power balance on the atmosphere in order to get out one equation, and then we'll do the same thing on the Earth itself and get out a second governing equation. So if we look at basically all the power flows here, and we have our assumption that the state of the temperature of the atmosphere changes instantaneously, then we get a balance here that the power coming in has to be equal to the power going out. And so we just write down essentially all the inputs. Sorry, here's an input. And then we write down all the outputs. And those are on the right-hand side. And we do a little bit of algebra, and I won't go through the details. You're welcome to look through this on your own. And then we get basically that the fourth power of the atmospheric temperature is going to be equal to the fourth power of the Earth's temperature divided by 2. Okay, so that's our equation for T of the atmosphere. And then we'll do a power balance again on the Earth's surface, but now we are assuming that the Earth's surface, all that water, has some thermal inertia. And so the temperature of all that water isn't going to change instantaneously. It's going to change somewhat more slowly. And so on the right-hand side, we have the difference between the power coming in and the power going out. And on the left-hand side, we have the basically energy, thermal energy contained in all that water that we're calling the surface of the Earth. So in math terms, we get du by dt on the left-hand side, where again, u was the energy. And on the right-hand side, again, we just take all the things coming in and we subtract all the stuff going out. And then we can simplify this. We know that u is equal to c times t, and c is a constant. So we can divide through by c. And then we get this thing here on the right-hand side. And this is a differential equation. And the state is T, basically the temperature of the Earth's surface. And you can see that it depends non-linearly on the state, right? The derivative is proportional to T to the fourth. So this is a nonlinear differential equation and a scalar version. Okay, so a little bit more physics or background, I guess. So what effect do greenhouse gases have on the surface temperature of the Earth? Well, in this model, at least, and it's a pretty good model of reality, essentially greenhouse gases increase the emissivity, that little epsilon that showed up in the thermal radiation that was being emitted by the atmosphere. And so if we take our governing equation here, our dt by t, little t thing here, and we set the left-hand side equal to 0, meaning we're looking for a steady state solution, and then we solve for t, we get this equation here that says t is the fourth root. So that's from undoing the fourth power of t that showed up in there. And then we have this stuff on the right-hand side, which, sigma here is a constant, s is basically a constant. The albedo of the Earth is fairly constant, although it changes a little bit. Like, so as glaciers are melting, for example, that alpha is going down because glaciers are really shiny. They bounce back a lot of sunlight into space. But emissivity, epsilon, this is really the thing that gets changed by greenhouse gas emissions. So if we, fix the values of all this other stuff and we just change epsilon, in the case where the atmosphere has emissivity of 0, so basically no thermal radiation interactions in the atmosphere, or essentially no atmosphere. That's basically that model. Then we get that the temperature of the Earth in steady state would drop to 255 Kelvin, which is about negative 18 degrees Celsius, or below 0 slightly Fahrenheit. So, so if the Earth had no atmosphere, like the average temperature over the year and over the space of the Earth would be below 0 Fahrenheit. And then if we take epsilon to 1, so this would be kind of rampant greenhouse gas effect or greenhouse effect, right? So if we took epsilon all the way to 1, then we would get an Earth's surface temperature of about 303 Kelvin, which is about 87 degrees Fahrenheit. So I think the average temperature over space and time on the Earth is kind of in the 50s Fahrenheit. I actually have that number, yeah, 57 Fahrenheit. So this was the pre-industrial average, basically before humans started emitting a lot of greenhouse gases and doing a lot of deforestation. So there, the average was about 57 degrees Fahrenheit, and that corresponds to an emissivity of about 75%. And then last year, or I guess 2022, the last year that I could find data for, the global average surface temperature was about 59 degrees Fahrenheit. And so that's consistent with an emissivity of about 77%. So you can see basically that by changing the composition of the atmosphere, we've essentially changed these thermal effects. And that explains the warming of about, I don't know, almost 1.5 degrees Celsius that we've seen so far. Okay, so here's a plot basically with carbon dioxide concentration on the x-axis, and this is in ppm, parts per million. And then we have two y-axes, a blue one and an orange one. And we have the emissivity of the atmosphere on the left-hand axis. And on the right-hand axis, we have global average surface temperature. And so you can see, and this isn't exact data, this is kind of a simplified linear model, but you can see that in, again, the pre-industrial era, we were at about below 300 ppm, and now we're above 400 ppm. And so that has caused both an increase in surface temperature and an increase in the emissivity of the atmosphere. All right, so that's just physics so far. We haven't gotten into any of the stuff that we talked about today for simulating differential equation systems and stuff like that. But any questions about the physics or the setup here? All right, so now let's use this as a sandbox to test out the things that we talked about today, the discretization of time and the linearization of the dynamics. So we have our dynamical system here, dt by dt, where big T is temperature and little t is time. And then let's assume that this thing, the albedo, is changing. And let's assume that we don't have control over it. So I don't know, this is something about ice formation, or I don't know, how shiny the Earth looks from space, clouds, things like that. So that's kind of random. We don't have control over it. But let's assume that we do have control over the emissivity of the atmosphere, because that's a proxy for greenhouse gas concentration. And we can control that basically by burning stuff or burning less stuff. Okay, so if we define U as little epsilon, and we'll define a disturbance that is related to, but not exactly, this alpha. And then we define X, the state, as just the temperature T. Then we get this nonlinear differential equation that describes the evolution of the temperature of the Earth. So here again, state X is equal to the temperature, the action we choose, the emissivity. And again, there's kind of this roughly linear relationship between the emissivity and the CO2 concentration. So you could imagine doing the same thing, but having the input be like the atmospheric carbon dioxide concentration, or maybe being actually the annual emissions that we produce as a society, something like that. And then, yeah, our disturbance, basically, I just take these coefficients and the stuff that's multiplying this alpha and pack it all into one variable, call that W. And then we define this parameter beta. It has no particular meaning. It just is a simplifying way to make shorter equations up here, essentially. Okay, so let's linearize first, and then we'll do the discrete time version, and then we'll do some simulations and compare this sort of full nonlinear thing to the approximate linear discrete time thing and see how it looks. Okay. All right, so first step basically is we can compute, basically come up with some nominal value, some nominal trajectories of U and the continuous time disturbance W tilde. And so I just kind of make up data for that, like make up whatever trends you want. And I'll share a MATLAB script with you guys that does this, and you can play with it yourself. And then we compute the partial derivatives. This was basically the way we've defined the system A and B in the continuous time linearized system. So I won't go through all the details there, but basically you can write down the derivatives. And we get this perturbation system here that has an A and a B in it, and a continuous time kind of disturbance term here. And then again, I'm just writing down kind of what those things are. But the main point is that we can do a little algebra and a little bit of calculus and get this discrete time linear system. Okay. And then we'll do, sorry, that was the continuous time linear system. Then we'll discretize, just choose a time step, delta t. I think I'm using like a year or something like that in simulations. And then assume all these guys are piecewise constant over time steps. Now, in reality, they're not, but that's fine. We'll just make that assumption, and it ends up being reasonably accurate. Okay, and then the discrete time system ends up having, the sort of perturbation system ends up having these discrete time dynamics, and you can again write down what the A, the B, and the disturbance terms are. And I won't go through those details because I want to show you some graphs and some code. But you can go through these slides and verify these calculations for yourself if you want. Okay, so let's go through these slides plot by plot here. So in each of these, the x-axis is time, and it runs basically from today all the way through 2100. And then the top plot here shows the atmospheric emissivity. And the dashed black line here is the nominal, indicates the nominal trajectories that we're linearizing around. So here, this is basically if we continue business as usual, more or less. We keep emitting carbon dioxide, concentration keeps going up, keeps driving up the atmospheric emissivity. We're on this kind of upward sloping trajectory here. Okay. And then the blue, so this is nominal, and the blue is what I'm calling true. So I want to simulate something that's not just sitting at that nominal thing. I want to be away from it so that we can compare how well the true solution, the full non-linear equation, basically how well our approximation agrees with that true thing. So if we sat exactly on top of the nominal trajectory, everything would agree perfectly, and it would be really boring graphs to me. So I'm doing a true thing that is further away from that. So this is like a slightly better trajectory, right? We're somehow decreasing the rate at which we're emitting CO2. And so the atmospheric emissivity isn't going up as much here as it otherwise would. And then, so second plot here is the atmospheric albedo. This is, again, basically how shiny the Earth looks from space. And so the nominal value there is exactly 30%, but then I'm assuming there's some kind of sinusoidal wiggles there that happen. And you can see here, I'm using kind of a stair step thing, and that's to just indicate that this thing alpha is piecewise constant over each time step. Okay, and then the bottom plot here shows the average surface temperature versus time, and in units of degrees Celsius. So you can see in the nominal scenario, it just kind of keeps going up linearly, pretty much linearly. And in the true thing, because this is lower than this, so the kind of average of the blue curve is lower than the average up here for temperature. And it's doing some wiggles, basically reflecting the wiggles that we see in the albedo. And then the dots here, this is essentially at the output of everything, all the processes that I described in the last couple of slides. So this is after linearizing and discretizing in time. And you can see that the pink things land pretty much on top of the blue curve. So even though we are no longer right in the neighborhood of the nominal trajectories, we're staying pretty much right on top of the actual state evolution. So again, the blue is using the full nonlinear equations to describe how the temperature of the Earth in this nonlinear model evolves. And the pink is the kind of linear approximate version. So you can see quite good agreement. And then the last plot here shows the prediction error between our linearized version and the true thing versus time. So one thing to note here is that the axis is in units of basically milli-degrees, so 1,000th of a degree. So you can see, first of all, that the scale of the y-axis is very small. So that says that the linearization here stays within basically 0.004 degrees of the true thing. But you can see that over time, we're getting more and more error, essentially. So it's always fine. It's always within a 1,000th of a degree, but the error is growing over time. And the reason for that is mainly that we're getting further and further away from that nominal trajectory that we linearized around. So you can think of this as like, oh, we're trying to send, I don't know, a rover to Mars or something like that. And we have some nominal trajectory. And as long as we stay near it, everything's cool. And we can use our linearized system to design, control of thrusters and things like that. But if we get knocked off that trajectory, by some weird gravitational event or something hits the satellite as it's, flying through space, then that linear description of the sort of nonlinear dynamics gets worse and worse. Okay, so now I just want to pull up the MATLAB script that I use to generate these files and play around with it a little bit. And I'll share the script with you. It has two subfunctions that do essentially the nonlinear simulation and then the linearized simulation. And so I won't share those scripts with you. Instead, I'll ask you to write them yourselves. Which basically will involve looking at the highlighted equations from these lecture slides and then programming them. Okay, so I start by generating some input data. So this is basically just writing down essentially the values for the albedo, for the emissivity, the solar constant, and so forth. And then I generate the time span. So we begin at time 0, and then we go up. I say the time step in units of seconds is basically 1 year, and so on. By the way, here I'm using what's called cell mode in MATLAB, which just lets you kind of pack your code into more readable chunks. So then this is where I drew that graph of the carbon dioxide concentration, the one that showed up here. And then here we do the nominal simulation. So I define this variable u hat, which is the action, the emissivity, kind of in the nominal scenario. And you can see that it's basically linear over time. And then I define the nominal albedo and the nominal disturbance here. So if we run this, we get just the beginning of the plot. So we don't have the blue or the pink stuff here. And again, I'm doing the simulation here by using this function that I've written called nonlinear climate sin. And what that basically does is it calls ODE 45 or 45. Okay, and then we do the true solution. So now I'm defining some u that is different from the u that we drew or that we use for the nominal scenario. So if we evaluate that cell, we get basically the blue stuff from the plot that I showed. And we can make it weirder. We can change, a plus to a minus, for example, and make it more extreme. So now we're actually decreasing. And we can put some wiggles on it. Make it kind of wiggle around here. And then, so that's the true code, or the true simulation. And then in the linearized thing, now again, we define the perturbations. So that's just the true input minus that nominal input. We define the perturbation in continuous time to the disturbance. Again, it's just a sort of a delta here. And then we run a linear simulation. And so this basically, you'll write yourself again, but it's using essentially the equations that I showed in the slides today. And so if you do this, then we get a couple of graphs that I showed here. So let me run the whole script again, just to get rid of some of that clutter. Yeah, so now you can see I put wiggles in this thing. Rather than just increasing more slowly, it's actually decreasing and so on. And then we get, in the true evolution of the temperature, we get this kind of weirder sort of sinusoidal-ish looking thing, but also doing this kind of linear decrease over time. And we're actually, we're staying quite close to the actual state here. But if we plot the error over time, you can see that the units actually are larger. So here we're about a factor of 10 further away than we were in that kind of simple nominal scenario where we stayed much closer to simpler scenario where we stayed closer to the nominal trajectory. So because we're getting further away from the neighborhood where everything is really accurate, our approximations are all really good. Therefore, the approximations are getting worse, basically. Okay, so again, I'll share this with you. You can play with it. You'll have to write those two scripts as part of a homework problem, but then you can change the inputs around and kind of fiddle with it and see what is interesting to you. Okay, so let me stop there. Are there any questions about today's lecture? Really about anything? Hey, very good. So good. I will talk to you guys then on Thursday.